Okay, thank you very much, Mike, for the introduction, and thank you very much to the organisers for inviting us to come over here. Thank you very much for coming. It's a beautiful day out there, so thank you very much. See what I have to say. As Mike says, I'm currently at University College London, which is the oldest chemistry department in England, and home to the first Nobel laureate, English Nobel laureate, Sir William Ramsay, who discovered the Nobel gases. Soon I will move to another university in England, in London, called King's College, the great rivals of University College, set up 2 years after University College. And today I'm an organometallic chemist. I take a quite pragmatic approach to research. It's often, I think, what I think I can make a contribution to with my knowledge base, and also increasingly what I think I can get funding for in order to pay the bills. And what I'm going to talk to you about today is the clean production of hydrogen. And in order to tackle this problem, we've taken some inspiration from nature. So that's the second part of it, biomimetics of an enzyme. So I really won't say much about this because I'm sure that you're all aware, acutely aware of issues about energy and CO2 emissions and energy security. But hydrogen is potentially a vital energy carrier. A lot of the alternative energy sources that are likely to come online, are coming online, are going to produce electricity. We are used to having chemical energy. And one simple way to convert chemical energy into electrical energy into chemical energy is through the use of hydrogen. And hydrogen is the most abundant element in the universe and potentially a nice, clean and safe fuel. Although doubtless the people on the SF Graf Hindenburg, Lakehurst, New Jersey, when it sparked and detonated, as you see on the bottom right there, would slightly argue. Hydrogen is rather difficult to transport and store, so one way around it is to generate hydrogen as you want to use it. And you can do that from electricity, a battery, and a proton source, an acid. And that's what we're going to talk about today. So it's a deceptively simple chemical transformation. I think that, you know, we deal with many complicated chemical transformations. And I would argue that we don't know quite enough yet about even the simplest transformations, but nevertheless, that is a great challenge in chemistry. And so here we have 2H plus 2 electrons goes to hydrogen, and for reasons that I'll mention a little bit later, both of the directions of this reaction, so mainly I'll focus early on is the reduction of protons to give hydrogen, but also the back reaction, the conversion of hydrogen into protons and electrons, as Jason mentioned, is a key component of a fuel cell. So I'll come back to that. So both directions of the reaction are potentially important. You could like many problems in chemistry, you can come at it from many different directions, and the direction that we and others, because I certainly don't exclusively work in this area, it's a very competitive worldwide area. A direction we've come at it is seeking inspiration from nature. We know that nature has catalysts. Nature has had millions, if not billions of years to develop these catalysts, and they are highly efficient, and we call them enzymes. Hydrogenases are a type of catalyst which can catalyze these reactions, both forward and back reactions, and hydrogenase enzymes are more efficient catalysts than platinum. And as Jason mentioned earlier, platinum is an excellent catalyst for a wide range of transformations, including the oxidation of hydrogen and the reduction of oxygen in fuel cells, but nevertheless it's totally unsustainable. Not just, even for the wealthy people on the planet is going to become unsustainable, you see. I mean, there are really two levels of sustainability. There's sustainability and the sustainability for the wealthy. And in the end, we will run out of precious metals. It may not be in my generation, it may not even quite be in your generation. I'm thinking about the younger people, but certainly your children or your children's children absolutely will run out of these metals. And that's going to place a massive task on chemists to replace those. And I'll come back to that in a moment. So when we look at these enzymes, of course nature is a great way to get inspiration, because nature only has earth-abundant elements to deal with. So when life was evolving, it can only use elements that are relatively abundant. And so when it uses metals, it uses the base metals, iron, cobalt, nickel, zinc, we've seen, small amounts of molybdenum, but otherwise it can't use these heavy, expensive elements, metals that we've been using. So nature's a good way to look for that. And with the advent of very powerful crystallography, we can now see the details of protein structures and therefore look at the active sites of the enzymes in quite some clear detail. And I'll come back to that again in a moment. And so what we wanted to try and do, we know the active sites of these enzymes, we know that they're highly efficient catalysts for these reactions. Can we go in laboratory and make cheap and functional, that means that actually carry out the catalysis ideally at rates that are not too dissimilar from the enzyme, although actually you don't need to get really as that good, but nevertheless carry at reasonable rates. Can they be prepared? And so that's our aim actually. So here are snippets of the active sites of three of these enzymes. Three types of enzymes. They have some similarities and some differences. All contain transition metal ions, so the metalloenzymes. All of them have an ion. Is there a pointer on? Is this a pointer as well? Wonderful. Thank you very much. Okay. So all contain a metal. All contain two centers. Now this has got two metals, two iron atoms. It's got an iron and nickel. This has got an iron and a redox active organic ligand. So what we're going to see is that the metals have different roles. One is going to bind protons and or hydrogen, and one is going to provide electrons or take electrons away. So even in the iron-only hydrogenase, these two iron atoms here, they play different roles. They also have unusual ligands for biology, and that is carbon monoxide and cyanide. Now normally, if you ask most chemistry students about carbon monoxide and cyanide, they will tell you they're very toxic and dangerous, and that is because they bind to our hemoglobin, and of course we need that for oxygen transport. Carbon monoxide and cyanide bind very strongly to hemoglobin, therefore we don't get oxygen transport, therefore we die. In a nutshell. Okay. However, nature's chosen to use carbon monoxide and cyanide. These are very, very ancient enzymes, arguably some of the first of nature's catalysts. And in the early Earth, when these enzymes were first generated, it was a highly reducing atmosphere, and carbon monoxide and cyanide were relatively abundant. And why has nature chosen to use carbon monoxide and cyanide? Well, as we will remember from our classical organometallic chemistry, these are soft ligands, pi acceptors, and able to stabilize metals in low oxidation. I'll come back to that. So what we're going to do, there are three types of enzymes. Most of the work by our group and others has focused on this enzyme, which is called the iron-only enzyme. This has clearly got iron and nickel. This has got iron. It's slightly confusing, but for many years it was believed that this didn't have a metal in. And it's relatively recently, about 2004, when that was shown to have a metal in. These around about 1999, 2000. So this is called the iron-only hydrogenase enzyme. Let's look at that in a little bit more detail. And here I don't want to give the game away too much, but I have no background in biology whatsoever. So proteins I just call spaghetti. And to me, I'm sure they're important, but I don't understand the importance of that. But all this spaghetti around here But then we get to the interesting bit for inorganic chemistry. The greens is iron and the yellows is sulfur. So we've got these iron-sulfur units, 1, 2, 3, 4, 5 of them. And when we look at these, they are split into 2 types. These 4 of these have Fe4S4 units. And these are very, very widely known in biology. And they're called ferredoxins. They come in slightly different shapes and forms as well. And it's quite well understood in these and other metalloenzymes that they can they can be utilized for electron transfer. So they consist of iron 2 and iron 3, mixed valence, and if we add electrons, the cluster can absorb those electrons. There are very small changes in the cluster, then it can pass them on, pass them on. These are like little molecular wires going in and out of the active site of the enzyme, which is buried deep within the spaghetti. There's also ways to get protons in, called proton channels, and I'm going to tell you about, but they're quite well known in biology. And of course, hydrogen can diffuse in or out. Hydrogen is very easy to diffuse, very small molecules can diffuse in that. But the interesting bit for myself and most inorganic chemists would be this small bit in the middle here, which is called the H cluster site. And here, this is this di-ion center that I showed on the last slide, here bound to COs and cyanide. So let's look at this, how chemists like to look at it with these line drawings, nice Lewis structures. And this is slightly simplified, but nevertheless we've got 2 ions here. We have a link through an amino acid, cysteine, to one of these Fe4S4 units, and I'm calling this the electron path. So electrons can come in here to this ion, and likewise they can go out as well. So this ion here is where we're putting electrons in and out of the system. And therefore, we surmise that the second metal center, ion in this case, is where protons or hydrogen bind. So this is our electrochemical site, and this is our chemical site. We have ligands like cyanides here. We also have dithiolate ligands, sulfur bridges. And these are all very important. I'm not going to go into it too much, but the key point is that we have this semi-bridging carbonyl, and there are a number of structures of the enzyme, and in different states. But this semi-bridging carbonyl is very important, and it is believed, let me attempt to show this, it's believed that the carbonyls have this structure, and this is an inactive form, and then as they rotate and one of the carbonyls goes bridging, it opens a vacant coordination site on this metal that can use in either proton or hydrogen binding. So the way to think about this, the enzyme is quite happy sitting there doing nothing until somehow it's activated. During the activation we then have a structural change. That then creates a vacant coordination site. Chemistry can happen very, very rapidly at that vacant coordination site. When the enzyme wants to switch off, it undergoes the structural change back to its inactive form. We're going to see just at the end of the talk that we can see that's clearly very important. And just to remind ourselves now, this normally in nature, iron 2 has a redox couple with iron 3. And of course that's what we think about when we have hemoglobin. But if nature doesn't want to go between iron 2 and iron 3, and it wants a different mechanism, for example, to go between iron 2 and iron 1, then it needs ligands that will not stabilize iron 3, and ligands which will support instead iron 1. And it's very well known, therefore, you use a pi acceptor ligand, a ligand which can pull electrons off the metal, carbon monoxide and cyanide. Okay, so both of these have that ability. And therefore, from that, we can surmise that it's clearly iron 2, iron 1 redox chemistry that's important, and we will not reach the iron 3 state. And how might this enzyme work? Now, this is again a little cartoon, almost certainly incorrect. I always tell students that when they have a mechanism, any mechanism for a catalytic reaction, even the best thought out ones, I stand and say, well, that's nice. It's incorrect. And I'm sure it's incorrect, even if it might be nearly correct and certainly conveys a lot of important information, catalysis is very, very complex. And when you change any variable like pressures and temperatures and concentrations, quite often, and people don't understand this, but quite often you switch slightly the nature of the catalysis. So that, but anyway, it still serves, it's useful for us to have a mechanistic cycle because it allows us to understand it as mere mortals, how these dangerous, how these very complex catalytic cycles may occur. And so what I'm showing you here is, here I've got iron 2, and we can show this from Mossbauer in the enzyme. This is the inactive, CO is blocking this active site, but we add an electron, we add it to this site because it comes in through the Fe4S4. So now one of the metals gets reduced. This has more electrons, and one of these carbonyls says, actually, I'd like to share some of this extra electron that you have. So it rotates into the bridging position. As it does so, it creates the vacant coordination site. Then protons come in here. I've shown one proton coming on the metal and one coming onto this nitrogen, which may or may not be the case. It looks nice, it's not necessarily true. But then it allows us, we have a H minus, a hydride, and a H plus, a proton. So there's an electrostatic interaction here, and therefore if we add an electron, we can see how we can create a HH bond, eliminate hydrogen, come back again. So one of the metals is acting as the place for electrons to come in and out if we do the reverse process. The other is for the binding of protons and hydrogen. I'll just skip over this very quickly. I think this is very important. Two things. What people say to me, why don't you use the enzymes themselves? And Fraser Armstrong at the University of Oxford, who is a very, very clever and bright scientist, uses the enzymes. It's very difficult to do. He attempts to put them on electrodes. The orientation of the enzyme on the electrode is key. Effectively, nature designs catalysts to having very impressive turnover frequencies. The train goes around the track very fast, okay, but relatively short lifetimes. The train doesn't stay on the track for that long. That's typically what nature does, because nature can't afford for the train to go round the wrong track. So nature tends to, the train's going, even when the train's still going around the track, the right track, it says, okay, you've had your time, you're out of there, next one's in. Because it cannot afford, if it goes very, very fast and catalyzes the wrong reaction, then that's very dangerous. And so of course, if we want something in a real application, we can give up something on turnover frequencies that we need to make up on turnover numbers. So how many times it will go around, how long will our catalyst last? It can't last seconds, it can't last hours, it needs to last at least days and ideally months and years. And also this comes back to our sustainability. This is an old now, but it plots the price of the precious metals, and of course these go up and down a little bit with the global recession, but nevertheless, you know, you've got platinum, 12,000 US dollars per mole, iron, 0.9 of a cent per mole. In the end, you want to not use platinum, you want to use iron or cobalt or nickel. In the end, you won't be able to use platinum, you'll have to use iron, cobalt, nickel. And the other beauty of using iron, cobalt, and nickel, for example, is that they are biocompatible. You know, there are biological processes to move them so to redistribute them. So, this is me looking for some interesting chemistry to do. I take a quite pragmatic approach. I think what we need to do is consider not to take nature too literally, but use it for inspiration. And so we've looked at all sorts. I mean, this is just some of the ones that we're looking at the moment. The obvious ones that I'll talk about look like the active site of the enzyme. This has got one metal on, because we can just put our electron in externally. We don't necessarily need to. This has three, because we want to build in ligands where we can protonate and then have a proton and a hydride, etc., etc. So there are many different, and I'm going to talk many different approaches we take. I'm just going to pick two in this area where we have simple ligands containing phosphine, some complexes containing phosphine. I'm certainly not the first person to do this, and I won't be the last. The Crystallography the Enzymes was published around about 1999-2000. Marcetta Darensberger, University of Texas. Very quickly, this is a complex that's been known since 1932. And she very quickly published an Angevanda paper on this as a structural model of the enzyme. So it's not basic enough to be a very good functional model. So that means, what it means is that it looks like the enzyme, but doesn't do what the enzyme does. Okay, it's like a model of a person, a shop dummy. I don't know whether you have those. It may be quite convincing for a while. From a distance, it may look like a person, but it can't do any of the functions of the person. The obvious thing, the problem is it hasn't got enough electron density, and we have 6 COs here. Very quickly, Tom Rashford swapped some COs for cyanide, and that looks very good because this is really what the enzyme, it has some COs and cyanides. The problem is here, when you add protons, it actually works as a catalyst for a short period, and then the proton finds a cyanide, and it latches onto the cyanide very tightly and deactivates the catalyst. Of course, in the enzyme, the protons do not approach the metal center in any random manner. They are directed through the proton channels. Now, if we want to have a catalyst, which is a cheap, robust catalyst, we can't do that easily. We'd have to have a lot of shrubbery in order to do that. So immediately it rules out having cyanides. So what people did, and I've given Sasha up, there's a number of people did this, but is instead of having cyanides, which are more electron releasing than carbonyls, you just have a phosphine. Now the beauty here is that the phosphine is neutral, and therefore protons won't bind to it, but nevertheless you can tailor the phosphine sterically and electronically in order to put electron density onto the system. And this now acts as a structural and a functional model. So let's just look at the key transformations when you're looking at this area catalysis. It's actually very simple compared to most area catalysis. There are 2 first steps that you can have when you're testing a new catalyst. Either the center is if the center's not very basic, then it doesn't bind a proton. And therefore, in order to start the catalysis, you must put an electron in. Really, you're mimicking nature in this respect, because almost certainly that's what the enzyme does first. And I've given that the term E. So it's an electrochemical step first. And then we generate some anion, which is basic enough to bind a proton, and off you go. However, if you put more electron donating ligands in, you push the electron density on the metal center, it becomes electron rich relatively. Now it will bind a proton. And so this is a chemical step, C. And of course, once you've bound the proton, this is pulling some of the electron density off the ion center, and therefore it becomes more easy to add an electron than in the neutral form. So you either got the first activation is either electrochemical or chemical. We'll see how that you can have both of those. So this is another look at the enzyme. I started doing this work in 2005. I actually ruptured my Achilles tendon and was sitting at home writing a review. And I started reading about this area of chemistry and became interested in it, and realized that people were doing a lot of these biomimics, but they weren't modeling a key feature in that these 2 ion centers are inequivalent. And a lot of the early models had them as equivalent. And so, and actually, just after I thought about this, Mike Hall came up with some theoretical work that said asymmetry of the diion center was a desirable feature of the biomimetic models. And so what we've done, and we've done a lot of work in this, but I've just tried to pull a couple of examples of what we've to illustrate this. We tried to see whether that was indeed important. So we have possible catalysts here where we've removed 2 carbonyls and we've simply added a diphosphine. Very easy chemistry to do. And either we can add it in a bridging mode where these 2 ions are equivalent but nevertheless relatively basic, or we can have it in a chelating mode, where these two ions are inequivalent. This one is more basic and therefore is likely to bind a proton more readily. This one is less basic and more likely to bind an electron. So it would seem fairly obvious that these are likely to be better catalysts than this, but nevertheless, we set out to try and show this. I say they can be relatively easy prepared. I'll just mention it briefly. And we make a lot of use of phosphorus 31 NMR and infrared spectroscopy to follow reactions, but ultimately we have a single crystal diffractometer that I run in our department, and so we rely a lot on structural chemistry as well. And so we can easily, certainly in the solid state, characterize these. This is a chelating isomer where the two phosphorus are equivalent. This is, I'm going into too much detail, this is a chelating isomer where they're inequivalent. This is a bridge isomer, we'll come back to that later. So we can easily characterize these. So are they catalysts? Oh yes, let me just say, if we're going to test this hypothesis, we need to have a method of preparing the two isomers in pure form, the bridge and the chelate. And actually that's non-trivial, and we've cycled through quite a lot of different ligands in order to be able to do that. And these work fairly well, these PN ligands, PNP ligands, and all we simply do, if we carry out the reaction of this hexacarbonyl complex and remove the COs using a chemical oxidizing agent, trimethylamine N oxide, which will remove CO as CO2. Then we can carry this out at room temperature and form the chelate isomer. If we then heat this in toluene, we can convert it to the bridge isomer. So we have access to the chelate and the bridge, and we can easily show that by X-ray crystallography. So the first thing we asked ourselves was, do they both undergo the same sort of protonation chemistry? We also did electrochemistry, and I'll come to that in a moment. But the key difference is in the protonation chemistry. So if you take the chelate isomer, now we expect these to be basic enough to bind a proton. We're pushing electrons onto the ion center, and indeed the chelates react with, in fairness, with strong acids to form very cleanly 100% yield these complexes where the hydride bridges the two ion centers. And these are very, very stable, etc. So this looks very attractive. In contrast, the simple, certainly with this ligand, if we try and protonate, we should have very, very similar basicity of our ion site, and yet we add the same acid, we have to add it much more in excess. The protonation is slow. We can get some evidence for something like this, but over the time frame of the experiment, it's unstable and decomposes. So this looks very unattractive to us. And so it looks like these sorts of catalysts are more likely in that their first step, this protonation, is facile and clean. I would say very briefly that if you can do this and monitor by crystallography, so this is the structure of the neutral and the protonated complex with one of the ligands, slightly different ligands. They are nearly identical, and all that tells me is that there's very little structural change upon the protonation. And that should tell me that there's a low energy for the protonation. However, it does hide quite a lot of chemistry, because you see that when we have the neutral ligand, neutral complex, it lies in this position, which we call the dibasal, but we don't need to worry too much about that. And when we have the protonated complex, it lies in this position, the dibasal. However, again, when we do NMR, we can monitor this protonation at low temperature. We do this quite regularly now, and here we see the first addition of proton results in the diphosphine moving into this new position, and we get this at -90, and as it warms between -60 and room temperature, the phosphine reverts back to its initial position. So you always have to be careful when you're doing chemistry and relying on structures. I'm trying to wake Mike up there, because quite often it can hide quite a lot of more complex structural rearrangements that can go on in solution. And even this is simple actually. We have others where we can at low temperature we can see two different types of terminal hydride. So we actually have 4 different types of hydride species in some processes, and yet it appears if you just look at the stable state of the starting material and the protonated complex that they're nearly identical. And yet you can see 4 separate structures as they cycle between these 2 states. And this is what I'm saying in catalysis. Often in catalytic cycles, often this level of detail goes unnoticed or unreported. And it can be important because occasionally one of those steps may have a high activation barrier and then something is just a poor catalyst. And I often see organic chemists, I don't want to knock them too much, but when they're screening catalysts, they just throw in one after the next. And then until they hit the right one, and they never really understand why that's the right one and why the others are not performing in such a good way. Okay, this is actually, we do a lot of this, and I've only got one or two slides on it. This is how we carry out the electrocatalysis. It's actually quite a nice experiment. There's a lot of information on here. Unfortunately, to someone like myself, I see these all day and every day. I do appreciate you haven't seen this sort of thing very regularly. It's a cyclic voltammetry, so it's simply changing the potential of the system, and there's lots of spectra overlaid here. But this black one here, with a little bump there, that is the neutral complex. And so we see a reduction, which we know is a 1 electron reduction, although from this simple information we don't know. And we come back around here and we see an oxidation that actually we're not interested in at the moment, but we use this as a nice characterization of the material, and all of the other spectra are the sequential addition of 1 equivalent, 2 equivalent, 3 equivalents, 4 of acid. And of course what happens is, if as we add acid, we have a catalysis, we reduce the protons, eliminate hydrogen, and therefore we reduce more protons, eliminate more hydrogen, and therefore we will have a current because more electrons are used up. So we don't, much to the annoyance of a lot of referees of our paper, measure the amount of hydrogen given off, because at the small amounts that we use, that's quite difficult, but we do know how much hydrogen is given off from the current, and we have a pretty good estimate. Okay? And so you can see as you sequentially add acid, you get a larger current, so it's becoming a better catalyst. So clearly it is dependent upon the concentration of acid. Interesting, you'll see that this is the potential of the neutral complex adds an electron at minus 2.3 volts. I've got it here. When we add acid, we know a proton binds, and therefore that should reduce the potential, and this is this potential here. We can do it in an independent experiment. That's at minus 1.7 volts. So this is catalysis from where we add a proton first and then add an electron, and then we don't quite know what happens after that. But there's also this large catalytic wave which is adding an electron first. And so clearly there are 2 separate catalytic, arguably if you see this little lump here, arguably 3 different catalytic processes that are happening in this same reaction mixture. But so let me try and say what they may be. The obvious one is this CE mechanism, where we have our neutral complex, we know that we can add acid, we go to this, then this adds an electron, and we can see this is what we're looking at minus 1.7 volts. But after that, that's the rate limiting step. We can't see what happens after that, but we make the assumption, right, incorrectly or incorrectly, that then that may be able to reprotonate and then elimination of hydrogen. So this is a CE, chemical, electrochemical, CE, chemical, electrochemical mechanism. But this second wave here is occurring at the first reduction potential of this complex, and therefore it must be the first thing is add an electron to give this anion, then protonation. We come to the same species, so then we say protonation and electron again. So this is an EC-CE mechanism. And presumably what's happening is as we add the proton, all of our complex protonates, all of it comes around, but when we come to this second reduction here, we must be at a higher potential, so we can now start reducing some of this. A little bit devil in the detail there, but I want to just show you that at least 2 catalytic cycles are operating at once, quite possibly more than 2. And this is where catalysis can get quite complicated. It's nice to draw 1 cycle, you'll rarely see 2 or 3 cycles drawn. And to cut a long story short, the chelate complexes are better catalysts, but not much better. And it's surprising, actually. Sometimes you don't want a stable complex. You don't. The hydride, I think, in the chelate is a little bit too stable, and it's too strongly bound. And so it's not always stable complexes which give the best catalyst. But clearly, it is the chelates are better than the bridging and have longer lifetimes. Okay, in the second, I'll move quite quickly through this. In the second bit, I'll just talk about the reverse reaction. This is some work the work I've just talked about. We published in Dalton last year, and this work has just been accepted for chemical communication, both RSC journals. Thank you, sir. Although all the enzymes, the three enzymes, can catalyze both the conversion of protons and electrons to hydrogen and the oxidation of hydrogen, the diion hydrogenase is most efficient for reducing protons and to hydrogen. The iron nickel one that I show here is much better at oxidizing hydrogen to give 2 protons and 2 electrons. We would love, and we have tried to do models of these. Unfortunately, you can spend an awful lot of time making complexes with 1 iron and 1 nickel in, and when you put them in the catalytic solution, or put them in a solution to do catalysis, at the end you find out you've got complexes with 1 or 2 ions in and 1 or 2 nickels in. So nature may be quite good at bringing together an iron and a nickel, but in our system, when we strip off all the spaghetti, the problem is we get rearrangement of the metals and we get iron complexes and nickel complexes. Martin Schroeder, who Jason used to work for, put a lot of effort into that. I'd say with little return, but he showed the rest of the community it's actually very hard to do. Recently I had a PhD student from Bangladesh come over, and he looked at it. Sometimes you get a fresh set of eyes and they look at the data you've already got in a different way. This just shows some oxidation behavior of one of our complexes, and you can see it has a beautiful reversible oxidation process. And he started thinking about these. We use it to simply characterize the compounds and show that they're not decomposing during the catalysis. But he said, actually, maybe if we add a second redox site to here, this is a nice reversible 1 electron oxidation. Obviously, to oxidize hydrogen, you need to remove 2 electrons. And so he said, if we add another redox site, which is actually exactly what the enzyme does, maybe we can get the back reaction using a diion compound. Now, unfortunately, while we were doing this, Tom Ramos had the same idea, published this work in Nature Chemistry, so we are the second to show this. But this beautiful complex involves about 10 synthetic steps, all of which are moderate to difficult. Okay, you have to make this pentamethyl ferrocene. Actually, you make a pentamethyl ethyl ferrocene. Anyway, what he showed was that this is indeed a catalyst for the oxidation of hydrogen. And what he surmised was that you needed a close relationship between the redox potentials of these 2 sites, this site and this site. Here's a ferrocene, and we all know that ferrocene can shuttle between the iron 2 and iron 3. So let me move quickly. This was our attempt. In fact, we'd made this complex in 2005, but I hadn't done anything with it. I just didn't think it was very interesting. And he picked it. I said, oh, we made this. Yeah, he said, what about, you seen this Rausch's plate? I said, oh yeah, we made a complex like that years ago, but we never did anything with it. And he said, oh, I think you should. So he did. And this shows the structure. It's a simple 1-pot reaction from something that you can make 10 grams of in an afternoon, and something which is commercially available, this phosphinoferrocene. So we simply add that, and here you've got 1 redox site, and here's the other. When you carry out, when you add protons and change the potential, you get proton reduction. So this is an active proton reduction catalyst. It actually, I'm not going to go into it, it works much, much better than the other diphosphine bridging compounds we had. And we now know that actually flexibility is very important in these ligands. But also it showed a 1 electron oxidation and then a second 1 electron oxidation. And I've just blown that up there, and we can think about the different redox states. But clearly we've shown this is oxidizing the diion center and this is oxidizing the ferrocene. We collaborate with a group in North Texas who do density functional calculations. And this is still work in progress, but this shows the highest occupied molecular orbital of the neutral complex, which is located on the ion-ion bond on the diion center. When you undergo a 1 electron reduction, you have a structural change, and one of the carbonyls goes into a bridging position, semi-bridging, which is important because it creates a vacant coordination site. This is a computer model, and now, as a structural change, you get an inversion of the HOMO, and now the ferrocene becomes the HOMO, and therefore you predict that the second oxidation would happen at this center. But nevertheless, if you're going to oxidize hydrogen, you still need electron transfer between this center and this center. And we're still working on that. This shows the data that actually what we're doing now is we add a base, and then we put hydrogen in, and we can see that the protons are generated, and we remove those with base. So again, this is how we monitor the catalysis. And this is actually behaving like the enzyme because it's truly doing the back and forward reaction. It's efficient in both. It's not the best catalyst for both, but nevertheless it can do both. And how do we think this might happen? Well, again, 1 electron oxidation of the diion center, semi-bridging carbonyl, oxidation at this center. We now need to have either hydrogen binding or electron transfer. First, we don't know. I put hydrogen binding here first. That's an absolute guess. Then electron transfer, and then loss of 2 protons. And I've got various redox states. I'm deliberately not dwelling on these because they're guesses at the moment, and we're trying to work out what sort of, but they're clearly mixed valence states, and you can draw things with ion 1, ion 2, and ion 3 in the same molecule. Now, whether that's stable or not, I'm not sure. So, anyway, I think in view I've used up plenty of time. I think hopefully I've shown you that we are making some progress in copying biology. We are the catalysts that we have are moderate catalysts, but not good enough at the moment to be used in any industrial process. The ferrocene one is potentially useful in a fuel cell because it's stable at 180 degrees. But there still are some technological issues to deal with. Finally, I'd like to thank various people that have funded us and various students that have done the work. Michael Richmond, I mentioned, he's a collaborator for doing calculations. David Unwin is a postgraduate who's written up his PhD now and did electrochemistry. Nathan Sushirita were postdocs. These guys, Shishi, I acknowledge especially, he's a current PhD student who did all the chemistry at the end there. Various funding agencies, and let me finally say, I'm moving to King's. We are in a beautiful site. We can't match Edinburgh for beauty and fresh air, I'd say, but if you really want to have a good time and have the world at your doorstep, this is showing the Arch Somerset House in King's College. The chemistry building is right here. This is the big wheel, the House of Parliament here, Trafalgar Square, etc., etc. So very attractive. And we run a course, chemistry with biomedicine. So our chemistry course is the only one in the UK, I don't know whether the only one worldwide, which serves to teach chemistry in a way that focuses on, it gives you the core chemistry, but also focus on applications in medicine. Okay. So with that, I'll say thank you very much for your attention.
Thank you, Graeme. So do we have any questions?
I think I've really overrun my time.
Well, we'll take one if somebody's feeling brave. Please.
It sounds very stupid questions, but you mentioned about, you show this iron 1, iron 2. Just wonder if actually they are discrete, or because in reality it's quite difficult to get iron 1.
Yes, no, that is very, I mean, absolutely very, very, very pertinent and good question.
Yeah. How stable they are.
Yes, they are almost certainly not discrete. Certainly there are two crystal structures, not from our work, but from Tom Ratchford's on an iron 1, iron 2 system, and it's clearly the electrons, clearly there's the EPR, it's clearly delocalized over the two centers. I really don't know with our system that we've done now. We are really doing calculations first, because the radical cation, although it has some stability, it's very, very easily reduced back. So we will work on that in due course. But you're absolutely right, the oxidation state, it's a non-trivial exercise.
Thank you.
Thank you very much. Okay, I think in light of time we'll move on. So please join me in thanking Graeme again.